In the last class, we were discussing about the DC machines and in particular the DC generator. We discussed about the structure of the DC generator, how a DC voltage, the unidirectional voltage is obtained. We saw that the DC machine is internally an AC machine with the currents and the voltages being an AC signal, and as it comes out of the brushes through a commutator, it becomes unidirectional and gets rectified. This we saw in the last class. We will of course consolidate our understanding of the DC motor further in this class. And just to have a quick review, we saw that in the last class, if we have a north pole and a south pole and a coil as shown here in red, the conductors near the north and the south pole will have the current directions out of phase, and these currents are going to be flowing through the external circuit through these brushes in black, through these brushes in black. Now, these brushes are in spring contact with the ring to which the coil is soldered. One end of the coil is soldered, the other end of the coil is soldered to another ring, and that is in contact with this brush. Now, here as the coil rotates, let us say this is the coil conductor A and this is coil conductor A dash. The current through A is positive, let us say this direction is positive, and as this comes into an orthogonal plane that is perpendicular to the north south axis, then the current through A and A bar will become 0, and then on further rotation the current through A starts going negative and the current flows in the opposite direction in the external load, and as it keeps going in this manner, it takes a sinusoidal wave shape pattern in the external circuit. And the induced EMF is given by the flux density B, the length of the conductor L, and the velocity with which the conductor is rotating and is cutting across the fields. So, that would be the induced EMF that one would be obtaining for every conductor, and there are two conductors and therefore, there will be twice as much. And then we also saw that to rectify the waveform here, one could use split rings, rings that are split as shown here. You see, these rings are combined to one single ring, but it is split in between. There is no electrical contact between the A side and the A dash side of the ring. Of course, the brushes are making contact, they are fixed, and through spring contact they are going to take the current into the external circuit. So, as the coil rotates, when it is at position north as shown here, the current is flowing through the brushes in this direction, and this is A and A dash, and here in this the current is flowing in this direction also, and as this rotates, the ring is also rotating along with the coil, and when this A portion of the conductor has come to the south pole side, which means we have A on this side, A dash on this side. Likewise, here also we have A dash on this side and A on this side, which means it has rotated. Yes. So, in A dash the current direction is as shown, and in the external circuit also the current direction is as shown. through the brushes. Whereas here the current, sorry, here the once this has made a rotation, this would have gone to this point, that is the connection here, because A is connected to that slip ring, and A is connected to this slip ring. Okay. So, now on the position getting interchanged, now A is at the south pole, like here. The direction of current in the brushes has reversed. So, here it is AC, whereas here it is unidirectional always. So, here you get a waveform pattern which is like that, and here you would get a waveform pattern which is about a 0 line, and this is about a 0 line. So, you get a unidirectional current as shown here, and this has been achieved due to this particular ring which we have put there, and that is called the commutator. Even here this unidirectional waveform pattern can be achieved by using electronically a circuit called the full wave rectifier. So, let us say we have a full wave rectifier diodes like this. We connect the diodes in this fashion and connect the load here, and this point is connected here, and this point is connected here. So, when the current is flowing in this direction, it will take this path, go through this load in this direction, and continue to take this path out into the A direction. When the current is positive here, that is when it has reversed the polarity, whereby the A is towards the north side and A dash is on the south side, we have a current which is flowing in this direction, which means we have a direction of current which comes opposite, goes in this direction and comes like that, which means through the load it is always the same polarity. So, you will have a waveform like this, unidirectional. So, a full wave rectifier diode bridge does the same job that the commutator was doing in the case of this machine. So, in this machine you do not need an external diode bridge, whereas in this machine to get a DC output you need a diode bridge. So, this machine along with the commutator is called the DC generator. It is called the DC generator. So, now let us consider the machine with the commutator as shown here. We would like to now represent it, because this becomes very cumbersome to write or draw in 3D and trying to put it into a. Let us now write a 2D picture of this DC machine. So, we have the north pole and the south pole. Now, the conductor near the north pole, there is one conductor in the north pole, we show it in this fashion. There is another conductor in the south pole. If you take the cross section, we show it in this fashion. The current flowing into the paper or into the board, current coming out of the board. This is shown in this fashion. Now, the conductor can't be just floating in free air, it needs to be wound over a coil, wound over a core, and we represent the core. There is a slot in the core through which the conductor passes through, and core is having a circular feature like this. Okay. So, this inner core is what is rotating, and along the shaft of the core will be these slip rings, will be these commutators. So, we shall put the commutator along the shaft of the core. So, this is the commutator, and then we have the brushes. So, let us say the brushes are positioned like that, and then out of the brushes we take two leads which go to the external load. So, there are two brushes, one for the positive and one for the negative. This is the brushes, and this is the commutator. Now, we draw a line, vertical line here, indicating that this half of the commutator is not connected with the other portion of the commutator, it is insulated. Now, this winding end, let us say, is A, and this winding end or coil end, which is A dash, this will be connected here and this will be connected here. So, this would be how a 2D picture of a DC machine will look like. Let us consolidate this concept or this idea of this DC machine with more coils. Also understand that a coil here, meaning that there is one conductor or one wire which is being routed through like this, but it could have many wires. It could have, like in a transformer, many windings like this, and the ends are brought out. Okay. So, keep that in mind. So, this is one coil with one set of conductors opposite ends of the diameter of the core, diametrically opposite end of the core. Now, let us have a look at the machine which is having 4 coils. So, let us have, as usual, the north pole and the south pole. Let us have a core which 4 slots. Let us first have a circular and to the circular core we shall have 4 slots. as shown here like this. Now, let us put in the coils. So, let us have one coil here, A dash, B dash. Let us have one more coil with opposite phase. Likewise, we have one coil here and one more coil with opposite phase. This means that if there is a coil, let us say A dash, and then another coil here B dash, then again one more set of coil, let us say C dash, okay, D dash, which means A and C are wound on the same slot, but having opposite direction of the coil winding. They are 180 degrees out of phase, which means at this point both these coils are near the north. Coil conductors are at the north pole, and the other part of the coil conductor is the south pole, which means if the A is having a direction of the current or an induced voltage in one direction, the induced voltage would be in the other direction because of 180 degrees out of phase. So, the voltage between these two coils is going to be double, and that is what is going to come across the brushes. And then in between we in this fashion. Four segments. So, the commutator is having 4 segments as shown here. Okay. So, now if the brushes are positioned in a manner like this, and we make the connection A here, A bar here, okay, and make the connection B bar, and then you have C bar, and then you have D bar cyclically. Now, this is still difficult to understand, this particular way of, but this is how it would look like in when you cut open the motor. Redraw this slightly so that it becomes more understandable for us from the circuit point of view. N. Yes. Now, let us have the commutator. The commutator being split into 4 Now let us start by placing the commutator always along the brushes, always along the axis which is perpendicular to the north-south axis, because on this axis there is no voltage induced. The voltage induced on this would be 0. So let us place the brush on this axis. Okay. And then so between this and this would be the A coil, let us say, which means this is A and this is A dash coil ends which are connected. They are actually in be diametrically opposite, but we are going to show this one as one single connection as such. And then between this and this we connect the coil B, let us say, this coil B with B dash. You see, coil share the same commutator segment, then B dash, then you have C dash, B dash and C share the same commutator segment, and then you have D dash. But notice that, but just be aware that B and B dash are two coil ends which are diametrically opposite on the core, but you are bringing it and then interconnecting it in this fashion. This is much more easier to understand from the circuit point of view. So the starting of the coil, you are starting at one commutator segment, the other, it is connected to the immediate next commutator segment, the other end of the coil. The starting of the other coil is starting from that commutator segment, ends on the next commutator segment, the next one starts at that same commutator segment, goes to the next, and so on and so forth. So this way the winding pattern for the 4 coils are shown. See that A and C coil will be 180 degrees out of phase, B and D coil will be 180 degrees out of phase. The reason we want to connect the brush here where there is no induced voltage in this line, at an instant when the position of the coils are like this, where A is in the orthogonal plane to the north-south plane, there is no induced voltage here nor here. There will be maximum induced voltage on the B and the D, that is, let us say on B you have 10 volts and D also you have 10 volts. So the voltage across the brushes would be, because these two are connected, so the voltage, the induced voltage would be 10 volts, would be 10 volts, because this is connected here, this brush is in contact with this commutator segment, this brush is in contact with this commutator segment which is at B, therefore it is 10 volts. The voltage across C being 0 at this point, the brush is shorting this coil C, and as the voltage is 0, there is no circulating current. Likewise, as this brush is shorting the coil A, which is on both sides of this commutator segment, and as the coil voltage A is 0, there is no circulating current in the coil. If suppose the brush were placed at any other position, then there will be some finite voltage across the coils which are across the brush, and that would form a circulating current, and the circulating currents can be pretty huge, and the I square loss would be very high. And therefore, it is advisable to place the brushes on the axis where the induced voltage will be 0, and this is called the neutral zone. The axis where there is no voltage which is going to be induced on the coils or the conductors is called the neutral zone, and they are always midpoint between the poles. So, if I am having circumference between the north and south poles, any two north and south poles, consecutive north and south poles, the midpoint is where the induced voltage will be 0, and that is a neutral zone, and the brushes should be positioned where the induced voltage will be 0, that is the brushes should be positioned in the neutral zone. Now, this here would give us, let us say this is E versus time. Now, let us say that the position is as such here, as shown here. So, D is having maximum 10 volts, let us say, the coil D. Coil B is also having 10 volts. What is appearing across the brushes is 10 volts, and let us just mark that as 10 volts at this position. Now, let the motor rotate anti-clockwise, the positive direction of rotation. Now, as the shaft is rotated, coil B comes to this position, that is the top position, and coil C would come to the position where the south pole is. So, which means coil C will now get 10 volts maximum. Now, what is happening to the voltage across the brush? As it is moving, the voltage across the coil B and coil D is decreasing, and voltage across coil C and coil A are increasing. So, at some point in between, even before it has come to 0, the voltage across coil C would have increased beyond, and the brush would take the sum of the voltages of the coils which comes between these two due to the commutator segments, and it will have a wave shape like that. In the case of the 2-segment commutator, but in the 4-segment commutator where you are having 4 coils, the coil voltages are like that. And because the coil segments are rotating, brush is coming in contact with the various coil segments, it takes the maximum of the voltages, which comes like this, and we see a lesser ripple. More the number of coil segments, lesser is going to be the ripple. If you have a 12 segment commutator, which means you have 12 coils, then the ripple is going to be still further reduced. So, let us have a look at how the schematic would be for a 12 segment or 12 coil machine. So, we continue to have the north and the south pole, the north and the south pole. Let us have a reasonably bigger diameter circle here, and we have the commutator which is now having 12 segments. The brushes mounted on the neutral zone, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have the commutator. There should be 12 slots on the core, the rotating shaft. As shown here. And these 12 slots, you need to have 2 coils out of phase with each other. So, you will have 2 coils out of phase with each other. So, we will have 12 coils which are connected in the following. So, let us put the schematic. So, coil 1, coil side 1 and 2. So, each coil is having 2 sides which are the they are on diametrically opposite ends of the core. So, let us say this is coil 1 coil, then the let us say A dash, and then another coil is connected in this fashion. So, like that you have 12 coils which are connected. So, at the given at a given point of time, the picture here, let us see the voltage. The voltage across this is going to be 0 volts because this is at an orthogonal axis with respect to the north south axis. The voltage here is going to be 0 volts. The voltage here could be probably, let us say, 10 volts. The voltage here is going to be 10 volts. Let us say the voltage here is 8 volts and the voltage here is 5 volts. The voltage here is 8 volts, 5 volts. So, you have 5 volts, 8 volts, 10 volts, 8 volts, 5 volts, symmetrically distributed. The voltage across the brush. So, the voltage across the brush, let me bring out the brush leads outside here. The voltage across the brush, let us say this is positive and was the negative, is, you see that all these conductors, all these segments are connected through the coils. So, between 2 and 3 you have 5 volts, 3 and 4 you have 8 volts, 4 and 5 you have 10 volts, 5 and 6 you have 8 volts, 6 and 7 you have 5 volts, and then between 7 and 8 0 volts. So, across the brush it is summation of this 5 volt coil plus 8 volt coil, 10 volt, 8 volt, 5 volt. So, that would lead to 16 plus 10, 26, 36. So, that will be 36 volts at this particular point. So, you will see that the ripple here will be much lesser than in the case of the 4 coil DC machine. Now, just imagine that what would happen. So, the brushes are no longer here, but instead the brushes are connected to these points. Now, you see that the voltage across the brush now is between 3 and 4 you have 8 volts plus 10 volts plus 8 volts, that is 26 volts, plus another 5 volts, which is now 31 volts for this brush position, which means the voltage across the brushes is going to be going to reduce, and further the brushes are shorting the 5 volts across the coil. In the earlier position, when it was 0 volts, when it was kept at the orthogonal position in the neutral zone, at that position any coil at that position would have 0 volts, and therefore it will not, brush will not short the coil, and even if it short there is no circulating current. Here, because the brush is not in the neutral zone, at the point where the commutator segments change over, the coils are shorted. So, the coil around at that point the induced voltage across the coil is around 5 volts, which means the 5 volts get shorted to through the two commutator segments because of the brush. So, it gets shorted through the brush here. So, which means there can be huge circulating currents in the coil winding, which could result in a lot of I square R losses. So, this is how the DC machine will look like, and the structure of the DC machine is in this fashion. At this point, it may be a good idea to have a look at how a real motor, the core of a real motor, the shaft of a real motor will look. So, let us have a look at the shaft. Before that, I would like to put in some. These are called the poles. These, as you know, are called the commutator segment. These are brushes. Now, these are the coils, and it is called the armature coils. Armature coils. This whole thing is the rotor. The whole thing is the rotor, which is rotating about a central axis. Now, let us the real motor or real rotor, how it looks like. Let us have a look at this rotor. This is the rotor of a DC machine. This portion, what you are seeing, is the commutator segment. This is again a 12 segment commutator. You have 12 slots on the rotor. These are the rotor slots through which the coils are wound, and there are 12 coils. So, the coils here are coming from the slots, from the 12 slots on the rotor, and you have the commutator segments. The coils are soldered onto the commutator segments here. If you notice, the coils are soldered onto the in the winding fashion that we just discussed. This type of winding fashion is called the lap winding. Now, this whole rotor will be mounted onto a central shaft, and then above that one will be another enclosure called the stator, which will have the poles and the north and the south poles. It could have more than one set of poles, and that would make the complete machine. This whole set together is called the armature. So, the armature consists of the core, and that is also laminated here, again because as we were explaining during the time of the transformers, the laminations are used to reduce the eddy current losses. This portion is the coil ends which are joined to the commutator segments. The brushes will come in contact at this copper surface of the commutator segments. So, the brushes will come in contact like that. It will be spring loaded. We will have a look at that in a different machine. You see that this is the armature which is fully mounted onto a yoke, and this is a complete motor which you see here. The shaft is capable of rotating here. So, when the shaft rotates, the commutator segments here, which are the coppery portions, make contact with the brushes. There are two brushes here on these two sides, and the commutator segments make contact with the copper coils by virtue of being soldered. Now, at this end there are very fine solder joints which make connection with the coils inside on the rotor, and this is a 38 slot motor, and therefore, you have much less ripple as compared to a 2 pole, as compared to a 2 slot or a 4 slot motor that we just saw. 4 slot meaning you have 4 slots on the rotor with 4 coils. 12 slots means 12 coils. 38 slots means you have 38 coils in this here. So, coming back onto the board, we now saw the structure of the DC machine, and in the case of the DC generator, the power comes from the shaft. This is the shaft, the mechanical shaft, which is in the mechanical domain, enters the DC machine. This is the DC machine, goes through the magnetic domain, and through the brushes, the power is fed to the external electrical circuit, through which the terminals of which is the load. It could be some load, or it could be a load impedance. Okay, we will come to that. So, this is a schematic of the whole DC machine, and we were looking at the internals of the DC machine, how it is structured, and how mechanical rotation can give rise to a voltage, and that to a unidirectional voltage or a DC voltage. So, if we have many slots, many coils per pole, then the voltage across the load, the induced voltage across the load will be almost ripple free. It will have negligible ripple across the load. And now, let us look at how much voltage is induced across the brushes. The induced voltage, we will call this one as E generated. E generated is given by N phi Z by 60, where N is the RPM of the shaft rotation or the rotor rotation. RPM is revolution per minute, revolution per minute. And phi is the flux per pole. This is in Webers. Notice that we have always put one pole set, one north pole, one south pole in all our discussions till now, but it is not necessary that it should be just one pole set. There could be many pole sets. So, the flux phi is the flux per pole, and Z is the total number of conductors on the armature, is the total number of conductors in the armature. So, the total number of conductors in the armature, the flux per pole, and the speed at which the rotor is rotating, they are linked to the value of the induced voltage or the generated voltage. So, the generated voltage E.g. is actually derivable from the alternate Faraday's law of electromagnetics, the equation which we have been using in the DC machines, E which is equal to B L V, where B here is the flux density, this is the length of the conductor, and this is the speed at which the conductor is moving, and this is given in meters per second. And from this we have arrived at the induced or the generated EMF E.g., which is N phi Z by 60. Now, N is the rotation, revolutions per minute, rotation of the rotor. So, rotation speed of rotation of the conductors. So, this is related to the V, velocity there. The number of conductors is related to the length of the conductors and the number of turns in the coil, and then the flux of course is related to the B. So, starting from this equation E is equal to BLV, the Faraday's equation or from the law of electromagnetics, one can derive this equation. Now, let us consolidate this understanding of this equation with a simple example, which will give us a better idea of using the equation. So, let us consider a DC machine whose armature has 6 poles. And the speed at which the armature is going to rotate will be 600 revolutions per minute. Now, this machine is designed to have 90 slots. By slots you mean, you see we were writing these slots, you remember, on the surface of the core, on the surface of the circular core. So, this was a 4 slot machine. Like that, let us say you have 90 slots, and each coil, the coil that is wound through the slots, has 4 turns per coil. That is, we used to always draw a coil with just 1 turn, but there could be many more turns than 1, and in this case this particular generator is wound with 4 turns. And the flux phi, which is 0.04 Webers, is the flux per pole. So, when given these information, what is Eg? The generated voltage or the generated EMF. So, Eg is N phi Z by 60. So, let us first calculate Z, total number of conductors in the armature. So, there are 90 slots, therefore, there are 90 coils, and there are 4 turns per coil, and 2 conductors per turn. For every turn there are 2 conductors which are diametrically opposite, 2 coil ends basically. So, this means this equals 90 into 4 into 2, which is 720 total number of conductors. The speed n is 600 rpm, and therefore, Eg is 720 into 600 rpm into 0.04 Webers flux per pole divided by 60, which is equal to 288 volts. This will be the induced EMF across the brushes of the generator of this particular DC machine, which has the specification as given here. Now, we know how to calculate the induced EMF across the generator. We need to look at the circuit of a generator and also the state equation that you would obtain for the following generator. The general state equation, that is in the form x dot is equal to x plus bu, y is equal to cx plus du, so that you can do any analysis on any type of generator, because all generators, DC generators, fall under the similar constructional principles and operational principles, and thereby they can be mathematically modeled. We will look at the mathematical model of the DC machine, DC generator. We shall also look at the voltage regulation characteristics of the DC generator, and the different types of excitation, that is how the pole or the flux is produced within the generator. And another important issue, and that is on the armature reaction, a concept which we have still not discussed, but we will discuss in the following session, the concept of armature reaction and how it is it can be avoided. Now, all these issues we will be discussing in the coming session. In this session, I would like to point out that the operation principle of the DC machine is quite simple actually, and the number of coils, the number of slots are increased so that you get a twofold advantage. One is the increase in voltage across the brushes, because each coil between the brushes there are now going to be more number of coils, and therefore the induced voltages of all these coils are going to add up and then come across the brush voltage, as we saw in the discussion today. And the second, a more important thing is that the voltage across the brush will have very less amount of the ripple as the number of coils and the slots increases. So, these two are the primary advantages in having large number of coils. Further, if the number of poles are also increased, then the ripple content in the DC machine, in the output of the DC machine will be negligibly small. So, we shall continue in the next class trying to consolidate on the mathematical model of the DC machine and the other aspects that I mentioned, like the armature reaction and the voltage regulation curves and the output curves. Thank you.